vectors and motion, and I'd like to talk about something called iterative methods, and to look at an iterative method for terminal velocity. Now, there's two situations where commonly you might get a question about iterative methods. There might be a mechanics one similar to this, or a capacitors one, and I've actually done a video about using iterative methods to look at charging and discharging capacitors. But let's look at this anyway. So terminal velocity, if you imagine we drop a small ball into a viscous fluid, imagine dropping a marble into a measuring cylinder full of oil. Can we calculate what its velocity will be at any time? What factors will affect the terminal velocity? Now, we could certainly do experiments. You know, we could drop different size balls, different mass balls, different viscosity of liquids. But can we actually model what's going on mathematically? And the answer is we can. Okay. Now, considering the forces acting on the ball, there's the weight of the ball, which doesn't change. The weight of the ball is just mg. But then we have these resistive forces, and the resistive forces are proportional to the velocity squared, where k is a constant, which is to do with something called the drag coefficient. The drag coefficient will depend on the surface area, it'll depend on the shape and the surface and a few other things. But let's keep it simple for the moment and just say that r equals kv squared, where v is the velocity. Now, the mass doesn't change, but does the terminal velocity depend on the mass? Well, we're going to answer that later. The acceleration, well, F equals ma, so A equals F over m. F, the resultant force, will be mg minus r. So mg minus r divided by m is g minus r over m. And that gives us this pretty horrible, what we call a differential equation. dv dt equals g minus kv squared over m. You know, and it's going to be pretty awkward to solve that thing, especially if you've only done A-level maths. Okay. However, there is another way of doing it, a sneaky way of doing it, and that is using this idea of an iterative method. What we're going to do is we're going to assume that for a small time interval, delta t, we're going to assume that the acceleration is constant. Now, is the acceleration constant? No, it's changing continuously. But if we say for a small time interval, delta t, if we assume that it's constant, then we can work stuff out. And the smaller the time interval we use, basically the less of a negative effect our assumption will have. In other words, the closer we will be to the actual values that we calculate. Now, we know that the initial acceleration is 8 meters per second squared. We know that this is going to get smaller. If we assume the acceleration is constant for a small time interval, then we can use v equals u plus at. And what we do is we do it in steps, and each step is delta t. For example, in this table, I'm going to use delta t is 0.05 seconds. And then for each small time interval, for each increment, we can then work out the velocity. Our initial value, of course, is 0. We can work out the resistive forces using kv squared, and we can work out the acceleration using 9.8 minus r over m. And then these values can be carried forward into the next row, and we can do it again and again and again. Very often, if you look at past papers, you'll see there's exam questions where you have to work out the first 2 or 3 rows in the column. Obviously, it gets tedious, so the best thing to do is put it in a spreadsheet. And that's what I've done here. I've got some initial values for k, and I'm using delta t as 0.05. I'm using a mass of 50 grams. So there's t, there's v, which is v is u plus at. R is kv squared, and A is G minus R over M. And you see here that the spreadsheet can work out as many values as you like. Does it actually work? Well, if we plot V against T, we get, and that I'm quite happy with that. That looks like a very characteristic kind of terminal velocity graph. The acceleration at the start is 9.8, but then it gets smaller and smaller, and it's tending towards 0. Okay. This is an important question. Why would using a smaller value for delta t give us more accurate values for V? And the answer is because, as I said earlier, we are making an assumption. We are assuming that for delta t, the acceleration is constant, and it isn't constant. The acceleration will be getting smaller. However, if we use a smaller value of delta t, then the assumption, if you like, will be more valid. The change in acceleration will be smaller. Okay, so it will have less of an effect, and we will get a more accurate answer. Now that I've got my wonderful spreadsheet set up and it's giving me graphs, I can very, very quickly investigate one or two things. I mean, how does the drag coefficient affect the terminal velocity? So I'm using a value of 0.05. What would happen if I made it bigger or smaller? Okay, well, K is 0.06. If I had a bigger drag coefficient, then as you can see here, my terminal velocity, not surprisingly, is smaller. So if there's more drag, then you have a smaller terminal velocity. Okay, which is, I suppose, how parachutes work. Another question, will an object with a bigger mass have the same terminal velocity? Well, originally I started with a mass of 50 grams, 0.05 kilograms. With my model, I can change that and see what difference it makes. And here we go. Here's 30 grams at the top and then 70 grams at the bottom. Okay, for 50 grams, it was just over 3 meters per second. For 30 grams, it's less than 2.5. And for 70 grams, it's more than 3.5. So basically, this tells me that a bigger mass would have a larger terminal velocity. Here's a question that I pose to my students. King Kong and a lady fall off the Empire State Building. Who hits the ground first? Now, one thing, hopefully you should appreciate that if there was no air resistance, they would hit the ground at the same time because they would have the same acceleration. However, we now know that the mass of the objects will have an effect. King Kong is going to have a larger terminal velocity because he has a much bigger mass. However, King Kong also would have a larger drag coefficient. Why? Because he's got a much bigger surface area, and I think the fact that he's very hairy would have something to do with it as well. So who would hit the ground first? And the answer is, I'm not sure. I mean, the only way is to find out.